We're going to be talking about regression. And when a scatter plot is showing a linear relationship between a quantitative explanatory variable, x, and a quantitative response variable, our y, we can use least squares regression fitted to the data to predict some y for any given value x. And we can do tests and confidence intervals just like we've done in the past. The slope and the intercept of this least squared regression line are called statistics. So in the past we've talked about stats like mu, we've talked about p, and now we're going to talk about b. And actually they're going to call it beta in our stuff. And these statistics change if we take a different sample, so that's why we're going to do some statistics on it. And we're going to focus on the slope of the regression line, and you're going to find that later in our lesson we call this thing, or the slope of the proportion, or the population, beta. And when we write it in our equation, when we talk about y hat, we usually talk about a plus bx, and this b is going to be the estimator of the slope from our sample. So suppose that we have n observations on an explanatory variable called x and a response variable called y. Our goal is to predict the behavior of our y, our prediction equation, our least squared regression line, for values of x. There are 5 things, I believe, 1, 2, 3, 4, 5, yeah, 5 things that help us to do that. And our book uses an acronym to talk about this. They call it LINER. So if you want a way to remember how to talk about all of these things, you'll find out that each of these things starts with a letter: linear, independent, normal, equal variance, and random. And LINER is the acronym they use to help you remember that. So the big idea today is going to be that we're going to have a population regression line. They call it mu of y, or the average y value, if you will, for some intercept a plus beta x. And this is the true regression line, like we've talked about in the past, true mean or true proportion, that kind of thing. And our slope is b, bless you. So this is the thing that we're going to be most concerned with in the yellow. We're going to talk about a lot of things to do with that, bless you. There's going to be some formulas that go with that. And so you need to know, first of all, that it's linear. The actual relationship is linear. We have things like probability plots. We have scatter plots to see, that kind of thing. We want to know that it's independent. We want to know that it's normal. We want to know that there's equal variance, or in other words, a standard deviation called sigma for the true regression line is the same for all values of x. And we want to know that it's random, just like in every single stats stuff that we've done so far. Let's move on to the next slide then. So on our next slide, the way that you're going to check these things is that LINER situation. So with the linear, what you're going to do is you're going to look at your scatter plot and see that the overall pattern looks roughly linear. Like, you do not want to see something that looks like this. Okay, because that's not linear. And you want to look at the residuals and to see that those center on the line 0. So if you remember when we did our residual plot, something like this, we would see residuals, and we would see that there was no pattern, of course, and then that they were all kind of roughly around the y equals 0 line. You want to know that they're independent and see how the data was produced. So that means you want random sampling and random assignment. That's usually in your plan design, which you're most of the time not going to have to worry about. If you don't replace things, like when you're dealing a deck of cards and I say, oh, you draw a card and you draw the jack of diamonds, because now you've affected the probability, now you check for independence with the fact that the population is 10 times the sample size. That's why we do that, because when you're pulling people out of the population, you want to make sure that you have a big enough sample and that the population is 10 times that. To check for things that are normal, you could do a stem plot. You could do a histogram, a normal probability plot. I'll demonstrate a couple of those in class either today or tomorrow of your residuals. You want to check for skewness, outliers, that kind of thing. Equal variance, you can look at the scatter plot of the residuals. We already talked about that a little bit. And then you want to see that your overall residuals is 0. So the same value that you're above that horizontal y equals 0 line should be the same total as below. That's what they're talking about. And the amount of the scatter should be roughly the same from smallest to largest values of x. So you don't want to be like one's way up and one's, close to the line, that kind of thing. And random, of course, again, you're talking about a random selection, which pretty much in every single problem we've ever done, they actually state that right in the problem. So down below here, there are some examples of some of the graphs that we'll be looking at. So the question is there a linear relationship between the height from which a paper helicopter is released and the time it takes to hit the ground? In an AP Stats class, we had an experiment to answer this question. There were 14 helicopters, and each of 5 drop heights, 152, 203, 254, 207, and 442 centimeters. The teams of students released the 70 helicopters, because 14 for each height. And predetermined random order. So there's our randomness. They measured the flight times in our seconds. And then we used Minitab, which is a calculator program. And what you're going to find is in this section, most of the time, not always, but most of the time, they're going to give you a computer printout. Remember those things that we had with the constant and then the whatever else label they gave and then SEB or whatever. So we're going to see that in just a little bit. And the class carried out a least squared regression analysis. And down below, you'll see a scatter plot. On the left here on the top, a residual plot. Over to the right, a histogram, bottom left, and a probability plot, bottom right. And I'll show you again how to do a few of those because some of those are like probably the residuals and the probability plot. You might have forgot how to do it. By the way, in your book, in the very back, if you ever forget how to do things on your calculator, they have a page that tells you how to do all those things. It tells you what page you're on, and it describes exactly what to do. The questions become, and this is looking back at the graphs on the previous page, we're going to check to see whether these conditions were met. Remember, there were 5 of them. Liner. There's going to be a little bit of writing, so you might want to get your hands limbered up. So the first condition that we talked about was linear. And the scatter plot shows a clear linear pattern and the residual plot is centered about y equals 0 and shows no curved pattern. Because remember, we're trying to make sure that there's no patterns there. You might recall from way back when we talked about this, we didn't want to see any other patterns. The second one was that, is this thing independent? Bless you. So for independence, they were released, the helicopters that is, were released in a random order. No helicopter was used twice. Which means it has no replacement. This means that no observation will give information about another observation. Good point. So on the previous page, question was about the scatter plot and its linearness. So if we're looking at the linearness, what they're talking about is right here, that these data points are following a linear pattern as we go along. These are scatter plots from the 5 different drops. So here's one drop, here's another drop, here's another drop, here's another drop, last drop. So this is the scatter plot right here. This is the residual plot. This is the probability plot. And this is the histogram that they were talking about. In case that wasn't clear before, I'm sorry. So number 3 on our list, is it normal? So when we're talking about normality, if we look at the histogram, it looks symmetric, bell-shaped, looks pretty close to normal. So the histogram is symmetric, bell-shaped, so it's approximately normal. We don't know if it's exactly normal, but it's approximately normal for sure. And then we wanted to talk about the equal variance, that was the E. And when you're looking at equal variance, you're looking at the residuals. So it looks like the residual plot shows a similar amount of, I guess what I call scatter around the line y equals 0 for almost all data points. If we look back at the picture really quick, the one that they're talking about is the one over here. It does seem like there's one way at the top right here that might be a little bit off. I don't know what that is. But that one looks a little bit farther away than some of the other ones for the most part. You might even have an argument for the fact, if you look farthest to the right, that maybe this data point is. But in general, they're pretty much centered around the 0. So that's our equal variance. And then the last thing is our information random? And so our helicopters were assigned one of 5, right? 5. One of 5 random heights. So if I were drawing a conclusion about all this stuff, I would say since all 5 conditions were met, I can do a confidence interval or test as needed. So if they want me to do either one, whether it's confidence interval or a test of significance, I can do either one, it doesn't matter. All my 5 conditions are ready to go. Okay, so now here's part of the math stuff. So all the rest of the stuff was about descriptors, looking at visuals and saying, hey, here are the conditions. In our new stuff here, when we're doing a confidence interval, which is what the next 2 slides are about, we approach this confidence interval really the same way we've been doing confidence intervals before, with all the different things, the state, the plan, the do, and the conclude. But there's some formulas that you have to understand. So the first thing that you need to know is when they're talking about the slope, or sorry, the confidence interval, we need to know something about the slope B of your population. So they're talking about this, the confidence interval. So confidence interval for the slope B goes like this. You have some statistic B, which is the slope of your sample, plus or minus your statistic, which is the t-score. Oftentimes when they talk about a 95% confidence interval, it's going to be 2. Plus or minus your standard error about your slope. And you're going to find that we're going to be using a table often, so it'll actually be given to you. You're not going to actually have to calculate any of this stuff. It'll be handed to you. And then, in addition to that,